this is going to be navigation and position determination. We have quite a few objectives in this module. We need to define the following navigation terms: course, heading, and ground track, nautical mile and knot, latitude and longitude. Given a map or sectional, we need to identify an object given its latitude and longitude, and given a position, determine its latitude and longitude. And then given a sectional chart, locate and discuss physical features, towns and cities, highways and roads, towers, like we mentioned before, airways, radio aids to navigation, things like VORs, and airports and airport data. Some other objectives, page 2 here. Given a sectional chart, we need to discuss the information found in the legend, which is very, very important. It's probably the most important part of the sectional chart. Given a sectional chart, we need to locate maximum elevation figures and state their meaning. Given a sectional chart, a plotter and 2 points on the chart, we need to determine the cardinal heading and determine the distance between the 2 points. So we're going to actually do a plotting of a course from Kahului to Hana, which is pretty simple. Given data from nav aids, we need to track the current position of an aircraft and determine the position of a ground feature. And state the size of a full and a 1/4 standardized grid. So our first task, locate a point on the map using latitude and longitude. So we have to define the terms first that were part of the objectives. The first is the course. So our course is actually our planned or actual path of the aircraft over the ground, which can be true or magnetic. The difference, of course, magnetic means that we're pointing towards the magnetic pole as north, and true is true north. So there's a difference because when you look at a map, you're looking at true longitudes and latitudes, and when you're in the airplane, you're following magnetic because you're following the compass. Heading is the direction the aircraft is actually pointing. The ground track is the actual path of the aircraft over the ground, and this is going to change because of winds. Nautical mile is the measurement of distance used in air navigation. It's longer than the statute mile, as Colonel Dennisig mentioned. It's approximately 6,000 feet. And then knots is the nautical miles per hour. So a knot is going to be faster than a mile per hour. So to give you specific numbers for a nautical mile, the nautical mile is actually 6,076 feet, while a statute mile is 5,280 feet, which is a difference of 796 feet. So you multiply a nautical mile by 1.15 to get your statute miles. Okay, so locating a position. So points are defined as x degrees of latitude and y degrees of longitude. So we use a system of imaginary lines. So anyone who's seen what we see here, a Mercator map, knows that everything is divided into perfect up, down, right, left squares. You'll see from the aeronautical maps that we use that these aren't actually straight up and down and left and right. So these vertical lines run north and south, which is the longitude. The horizontal lines run east and west, which is the latitude. And where they cross defines a point on the Earth. And then by convention, latitude is stated first. So we always say x degrees of latitude and y degrees of longitude. I'll talk about latitude first. Lines of latitude run east and west. The line in the very middle is the equator, of course, and it's the great circle, and all other lines of latitude are lesser circles. If we look at the actual globe, you'll see that each line of latitude is actually, the diameter becomes less and less as we go up. And the Mercator map kind of distorts that by flattening everything. Latitude starts with 0 degrees at the equator and increases to 90 degrees at the north and 90 degrees at the south pole. And then, of course, there's longitude. The longitude has a place to start. It's called the prime meridian, which goes through Greenwich, England, which is 0 degrees. And the longitude goes east and west. So typically when we go west, we're talking about negative numbers, and when we go east, we're talking about positive numbers. So west longitude, east longitude. So where we're located is, because we're west of the prime meridian, we're going to have a longitude that's going to be a negative number. So again, Greenwich is the prime meridian. East-west longitudes increase till they meet at 180 degrees on the side of the Earth, and all lines of longitude are great circles, same thing.
What I want to point out is the format that we're using for the latitude and longitude, because that's real important and that can cause confusion. I've seen it happen before. Notice that the format is in like north, if we look at the latitude, is it in degrees, like 20 degrees, and then the next thing is minutes. So what's a minute? A degree is divided into 60 minutes. It's kind of like a clock, you know, we got 60 seconds in a minute and 60 minutes in an hour. Well, they've done the same thing. The latitude would be north 20 degrees, 47 minutes. And then if you want to specify it more precisely, then you use fractions, decimal fractions of a minute. because there's another convention out there. There's a couple ways. One way you could do it is you could go north 20 and then a decimal fraction of degrees. So it might be something like 0.78, 20.78. But that's not what we use. We use degrees, minutes, and then decimal fractions of a minute. Same thing in the longitude. The longitude is 156 degrees, 57 minutes, and then no fraction of a minute beyond that there. So particularly if you're dealing with another agency, sheriff's office or police or fire, they might use a different convention, and as a result, there can be confusion as to location. So again, bottom line, degrees, minutes, and decimal fractions of a minute is what we use in CEP.
So now we're going to try to find a location. And so here's a map of Oahu and Kauai. What's the latitude and longitude? So see these little red circles? So let's say for this spot right here, for instance, right? Basically, we've got our longitude, which is here, and we see 159. When we report this, it's actually negative 159 because we're west of the prime meridian. And then this is 22 degrees. North is the latitude. And so that's this point right here. And so basically we would report this point as it's going to be a larger number, but more negative than 159. And it's going to be a smaller number than 22. I'm not going to ask you for the actual, we've got that coming later on. Just kind of an example here.
So I want to explain the CEP grid system. First of all, I will say that we do not use the CEP grid system in Hawaii. So you may be asking, well, why are we talking about it? Well, the reason we're talking about it is we're not making you Hawaii scanners, we're making you Civil Air Patrol scanners. So you need to understand how this system works elsewhere. And this is the northwest corner of the state of Washington. On the very bottom, if you'll look, you'll see 48 degrees. So that's the 48-degree latitude line. So right here in the lower left corner is the latitude line for 48 degrees. So it goes across the bottom of the map there. Some of you that might have lived in the mainland will know that the 49th parallel, right here, 49 degrees is labeled, is the latitude that separates Canada from the United States for the most part, except when you get around the Great Lakes. So this is basically 1 degree of latitude. And remember, 1 degree can be broken down into 60 minutes. And every minute is equal to 1 nautical mile. So from 48 down here to 49 up here is 60 nautical miles, which would be about 69 statute miles. So the CEP grid system, so we can assign areas for searching. The way they did that is they take these squares, which are 1 degree in latitude and also 1 degree in longitude. This is 125 west. This is 124 west. So they take this 1 degree by 1 degree square, if you will, and they break it down into 15-minute intervals. So there'd be 4 15-minute intervals in 1 degree, because 15 into 60 goes 4 times. So that's 15 minutes, that's 15 minutes, that's 15 minutes, and that's 15 minutes. And same thing the other way. This is 15 minutes of longitude, 15 minutes of longitude. So this is a CEP grid. And what they do is on these sectional charts, these maps, they have them labeled for different primary cities. And this happens to be the Seattle sectional. So for the Seattle sectional, the very northwest corner is labeled Seattle 1. And then when you go to the next 15 degree by 15 degree square, that's Seattle 2, Seattle 3, Seattle 4. You go all the way to the end right here at the very east side. This is 32. So that's 32 of these CEP grids. And then you start getting into another map, which is the Great Falls map. So then that's they just go in numerical order. And then they drop down and start again. So now you got 33, 34, 35, 36. So, and so on, and they just keep going there. So a CAP grid is 15 minutes of latitude and 15 minutes of longitude. That's a standard CAP grid. And then they break down a CAP grid into these quarter grids. So here you see the Seattle 1 is broken down into 4 quarter grids labeled A, B, C, D. And every grid is similarly broken down into these quarter grids. So a quarter grid, if you think about it, this is 15 minutes. So a quarter grid is going to be 7.5 minutes. So that's 7.5 minutes of latitude, 7.5 minutes of longitude. And of course, the farther north you get, the smaller your minutes of longitude become, because these lines approach each other as they approach the North Pole. So 7.5 minutes in latitude is how many miles?
7.5.
7.5 miles, that's right, because every minute of latitude is 1 nautical mile. So it's exactly right. So this would be 7.5 miles. And just looking at this, roughly, I think it's roughly about 5 miles at the latitude of Washington State, which is up around, as we know, 48, 49 degrees. So 7.5 miles by, what did I say, 5 miles? So that would be about 37 square miles. So that's still quite a bit of area. Typical assignment, if you're searching a grid, would be to cover maybe 2 quarter grids. So you might do Seattle AB or Seattle AC, something like that. So let's talk now again about latitudes and longitudes. Here is an area that's north of Kauai. And you see here, this is the 22 degree parallel, 22 degrees of latitude. Here it's 23. Longitude here is west 159 or minus 159, like Daryl said. You'll see that referred to sometimes. And here is 160. So the first thing, let's see if we can figure out this spot right here, the little dash that I got circled with red, what the coordinates are of that point. And the way we're going to do that, I'm going to put this ruler, and all you do is you need to put a straight edge there. And then I can take a look over here and see what my latitude is. So this is 22 degrees. This is 23. So this is going to be 2230, right? There's 60 minutes in a degree. So that's 2230, 2240, 2243. So we would write the latitude as north 22-43.0. Similarly, we would do, and as Daryl said, we always talk about latitude first by convention and then longitude. So now we know the latitude of that little dash in the warning area. So now we're going to take our cursor and we're going to run it the other way to determine what our latitude, our longitude is. I put that right over the point, and then I can look up here at the top. This is 159, this is 160. That would be 159.10, 159.20, 159.30. So that would be 159.17. So that's west 159.17. So now your challenge is to take a look at this dash over here in warning 188 Bravo and tell me what the coordinates are of that point. So I'm going to give you a minute to do that. Let me try to get this blown up as best I can for you there.
Are they going for, in warning Whiskey 188 Bravo, are they going for a specific point in that?
That dash right there.
That's the dash, okay.
Yeah. Okay, well, let's see how we're doing. Starting with the latitude, what is the latitude of this point in the ocean right here?
North 22 degrees, 45 minutes.
Okay, who's that?
James?
Yeah, you're exactly right. North 22 degrees, 45. I had 45.5 because I could measure a little bit more accurately, but yeah, that's exactly right. Perfect. Okay, how about longitude?
159 degrees, 48 minutes.
Okay,
Or,
nice.
yeah,
Okay,
yeah,
so you guys got it figured out. Now, you might see just the opposite. Instead of starting with a point, how about if I were to give you something like north 22 dash 45 by west 159 48. Those are the coordinates there. So you'd plot the, well, I'll just go through it. So let's say it's north 22 45. So I'm looking here. There's 22. There's 23. So 2245, well, that's 30. It's going to be halfway up. So it's going to be right along there. So it's going to be a line. We'll go ahead and put a line there, right about there. So we know it's somewhere along that line, but we don't know exactly where it is along that line. And you can use a pencil and actually put a light mark on a map if you need to do that. So that's the latitude. And then we said the longitude is 159.48. Okay, so there's 159. There's 160. So now we want to go 48 degrees. Well, that's 30. That's 40. That would be 48 right there. So I want to put a vertical line right there. So if I put that vertical line there, you see where it intersects the dash in Whiskey 188 Bravo. And we already had earlier a horizontal line. I can't draw two lines at once, unfortunately. But that gives you the idea there.
And we're going to switch to sectional charts now. So using the sectional charts. Okay, so sectional charts are typically 1/500,000th of their actual size. So 1 inch equals 6.86 nautical miles. They point out contour intervals and how old the topographic data is. They show cultural or man-made features like cities. If anybody has any of these maps, they can take a look at it. The left panel is legend, and the right panel is the front page. This is our Hawaiian Islands map. You can see the effective dates, 23rd April 2020, and it expires 8 October 2020. The legend has all the important information that's going to be on the map. So the legend is often overlooked, but vital part of the sectional. It's written explanation of the symbols, projections, and other features used on the chart. Other important areas of the chart are its title page or the panel, okay, and it has a picture of actually the area that the chart covers and information on where the chart covers. So here it's Mariana and Samoan Islands is for this one, and then there's the Hawaiian Islands one's part of the sectional chart as well. So here's an expanded version of the top part of the legend to show that it shows different types of airports. So you've got everything from your larger airports here to your smaller airports, 1,500 feet to 8,069 feet in length. A lot of other information about airports here, whether it has a heliport, there's abandoned airports, ultralight flight parks, whatever might be important to annotate on the map. On the right side over here, we see airport data, and the airport data gives us a lot of pertinent information about the airport. The most important information here is going to be this number here, which is the elevation of the airport. This number here, which is the length of the airport. So we're looking at, this is in hundreds of feet. So you're looking at an elevation of 285 feet with a airfield length of 7,200 feet. So these are the two most important things on this chart here for the airport. So on this part of the legend, which is the bottom half, shows things like airspace, and then you've got airways, and then you've got borders for things like prohibited, restricted, warning areas, those kind of things as well. And then over here, which is very important, are the obstructions. So these are going to be things like towers, multiple obstructions, which could be buildings, wind turbines. So a lot of information on the legend that's going to be very important when reading the sectional chart. Okay, so when reading sectional aeronautical charts, and this is a picture of blown up of Oahu and its airspace, you should be able to locate airports, define airspace, be able to point out nav aids, airways, obstacles, and towers. All from this enhancement of Oahu airspace, you can see all these different things. Larger airports are depicted with outlines of the actual runways. So for instance, Honolulu has an outline runways. And so if we look back at the legend, we'll see that they denote that one of the runways is at least 8,069 feet. Again, as I mentioned earlier, runway lengths are typically written as a number showing elevation, then an L if lighted, followed by a number showing runway length in hundreds of feet. So Honolulu's longest runway would be 12,300 feet. And you've got Kalealoa here, which is 8,000 feet. Airports shown in circles have runways less than 8,069 feet. So a good example is right here, Kaneohe. So airspace denoted by dark shaded lines with solid blue showing are Class B. So these blue lines here show Class B airspace. Graduated thick purple lines show the limits of Class E airspace down to 700 feet. So it's graduated lines here, like this. And dotted blue lines show Class D airspace. Dotted blue lines would be right here. Dotted purple lines will show Class E airspace to the surface as well. So you can see how confusing the map gets when adding different floors and ceilings of each of the different airspaces. So if you look at things like for instance, in Honolulu's Class B airspace, there's floors and ceilings denoted by these, they look like fractions. And basically the top number is the ceiling and the bottom number is the floor. So that means this airspace actually exists from 1,500 feet to 9,000 feet. You need to learn about nav aids. So the most important nav aids here are going to be, so an example of a great nav aid here is Coco Head, which is a VOR, and they're denoted with these symbols here, and you'll find that in the legend. There's also maximum elevation figures, which you need to know as well. That's the MEFs, and maximum elevation figures are like this here. So that means in this quadrant, away from Honolulu Airport, maximum elevation of anything is 3,900 feet. And here's 3,500 feet. Airways shown in blue shaded lines that have a direction arrow are determined by a set number of degrees from a VOR and have indicators starting with the V. So for instance, here, V16, this is an airway. And basically all of these blue shaded lines are going to be airways, V12 here. Obstacles are shown with blue triangles with a dot in it. So that's like these things here. So if you see these things with multiple triangles with dots, and you see that it's here in Honolulu, you know that these are going to be tall buildings, and it shows the heights here, 519 feet, 406 feet, those kind of things. So anything under 1,000 feet is going to look like these little mountains, whether they're single mountains or they're multiple mountain kind of things. While anything that's over 1,000 feet tall will look like this. They'll look like these tall towers. And so these are, I guess, radio towers that are 1,504 feet tall. There's so many different things that you have to know about sectional chart. But by looking at the legend, you can quickly decode everything. It tells you how to decode, for instance, what this is. That means it's a parachute area. What this symbol means, glider operations, parachutes. And then you've got all kinds of different things like alert areas, restricted areas, etc. So I've blown up the section just over Honolulu Airport. Given a sectional chart, you need to be able to locate and discuss physical features such as topographical details. Topographical details are just like, topographical details in any kind of map. You're going to see these different kind of shaded areas and different elevations of the land. Towns and cities. So in sectional charts, towns and cities are denoted by these yellow areas, and those are typically areas of high population. Highways and roads. So if you look very carefully, you didn't see it in the broader view, but when you get closer up to the map, you see all these gray roads here. These are all roads and highways. Towers, we talked about it before. They could be, buildings, or they could be the tall tower symbol or whatever that we saw on the wider view. And basically the towers show their heights in MSL and HEL. So MSL is height over mean sea level, and HEL is the height above the ground level. Airways and radio aids to navigation will be shown on the map. So we can't really see it here, but actually Honolulu has a little dot in here, which basically says that there's a VOR here. And then we've got airport and airport data, which is again down here. And those can all be decoded with the legend. Everything from the control tower frequencies, so CT is control tower, these are the frequencies. The ATIS, which is the weather frequencies, that's these frequencies. You've got their names, HNL and PHNL. Again, you've got your height above sea level. You've got the longest runway, which is 12,300 feet. L is lighted. Going back out to the bigger view of Oahu, I'm going to start talking about restricted areas, military training routes, and military operations areas. So we have a ton of restricted areas in Hawaii, which covers almost all the open ocean northwest and south of Oahu, either used by the military for training, or they're just places where there's nobody keeping an eye out on you. So you've really got to be careful about going out into these areas. Restricted and warning areas are denoted by the blue feathery boundary. So see these blue feathery boundaries here? These are restricted and warning areas. Alert areas are denoted by feathery red areas. So you got an alert area, a big one here, and it has a number A311. So warning areas are typically extend from 3 nautical miles from the coast of the US, but are different defined areas here in Hawaii. It warns that there may be activities happening that may be hazardous to aircraft. Again, things like military training or just nobody's looking out for you. Military training routes and operation areas are places where there may be high-speed military planes doing training, which can be a hazard to any plane coming into the area. So as far as I know, Hawaii doesn't have any military training routes. Do they, Lieutenant Colonel Denize? It's just they do practice out in the warning areas, yeah, in restricted areas.
Well, MTRs would be just black lines, and they'd be like an IR or VR with a couple of numbers.
Yeah, so, but we don't have any of them in Hawaii, I don't think.
No, there aren't any.
Yeah.
So you won't see that, but it's good to know for those that want to be pilots.
Yes. Okay, great. And so let's see. So yeah, military training routes and operation areas are places where there may be high-speed military planes doing training. And they're, again, yeah, as you mentioned, they're in gray lines and they can be pretty heavily used. So it's always good to kind of stay away from those. They are a hazard to any plane coming into the area. Alert areas may contain a high volume of pilot training or other type of aerial activity. So that's this alert area here. Restricted areas require permission from center. So if it's active, you will not be given permission to enter. Warning areas is best to just stay out of, and its entry is at your own risk, as you must stay away if it is active. Military operation areas, so we didn't talk about military operation areas, but in places like Florida and in California, you'll see huge swaths of land that are MOAs. And the interesting about MOAs is that these are places where the military is doing a lot of training. The interesting thing is that as a pilot, you can fly into these MOA areas without talking to anybody. It's not advised. If you're flying IFR, that's instrument, through a military operation area, usually the center will plot your path through so that you stay clear of any kind of training that's going on. But if you're flying VFR, which is what we're doing most of the time, if you're flying VFR, then you're looking out for yourself. You have to look out for possibly fast-moving aircraft doing training, all those kind of things, and it's very dangerous. So if we're going to fly through an MOA, even when it's active, it's always good to talk to center or to talk to the controlling agency to see if there's any activity going on, just to be sure, or to stay out of the area as much as possible. So MOAs and alert areas do not require permission, but it's not safe to fly in them. And here's an example of a military operation area. So this is the Red Hills MOA. And as I said, when you get to the mainland, you'll see these huge swaths. And it's always best to just stay out of them, even though you can actually fly into them if you wanted to. The typical way to stay clear of planes if having to go through an MOA is to get flight following from the nearest air traffic control, and make sure the MOA controllers know your intentions and you're in contact with them when transiting the MOA so they can keep you away from traffic. I guess a lot of people might be a little bit confused with what airspace is. So the United States and actually the entire world works under a very strange and sometimes not so intuitive classification of airspace. So airspace is classified from A to G. In the United States, we don't have a Class F, but if you go outside the United States, they do have Class F airspace. What it is, I have no idea because we don't use it here in the U.S. So Class A airspace extends from 18,000 feet above sea level to 60,000 feet above sea level. When we get to these levels of altitude, we usually don't talk about 18,000 feet or 60,000 feet. We usually say things like flight level 180 or flight level 600, which is 60,000 feet. And you can only fly Class A if you and your plane are IFR equipped. Class B airspace, an example would be Honolulu's airport, which is our only Class B airspace airport in Hawaii. We like to use the moniker busy for Class B. This surrounds the busiest airports from the surface to typically 10,000 feet above sea level. So the way it works is that the airspace is divided into layers like a cake. So you can see that it's kind of like in a V pattern. And that's just so that they can keep control and track of planes coming in for landing and taking off. Class C airspace, an example is our airport here in Kahului. The moniker we use for Class C is communications. Basically what it means is that we have to have two-way communications with the airport, and they typically also has a multi-layer cake airspace. Class D airspace surrounds smaller airports, and as you saw before, you saw the little kind of dotted blue lines. That was the Class D airspace. They typically have they have to have control towers, and it extends from the surface to typically 2,500 feet above sea level. Good example of a Class D airport is the airport on Molokai, the main airport on Molokai. Class E airspace is controlled, such as airspace that surrounds instrument approach paths or federal airways in all other locations other than Class A, B, C, or D airspace, and basically includes everything except for the Class G airspace. So Class G airspace is the uncontrolled airspace. And here in Hawaii, I think Class G airspace, the only uncontrolled airspace we have is the airspace below 700 feet above ground level outside of airports. Okay, great. So back to track and record position on sectionals and maps. Position determination, sectional or map. So we work from larger to smaller. We work from a known location to a present location. We need to watch the scale on the maps, and we need to remain suspicious that all the points don't seem to line up right. We typically use 3 characters to verify position. Let's try to plot a path between Kahului Airport and Hana using this E6B computer's sectional ruler. How do we do that?
Well, the first thing would be to draw a course line from your departure airport to your destination airport.
So is this how we would plot our course to Hana?
When you plot your course, don't you want like a straight line so that it's easier?
So what we would typically do is we would use our ruler and draw a straight line, and then we would use our plotter, which is actually on the other side of this. There's a little circle that you can turn and tell which direction you need to fly in. Here on the chart, though, we can do it by just looking at the airport. So on the airport here, we have 0 degrees here, 30 degrees, 60 degrees, and this right here would be about 90, maybe 95 degrees. Let's see if I can draw a straight line. There we go. So we can see that the course line goes right between, so this is 12, 11, 10, 9, so right between 9 and 10. What heading would we be going?
Well, actually, your course would be 095 degrees. The heading would depend on the wind.
Exactly. So the course is 095 degrees, but the heading has to be changed for the wind. And there's actually another trick question to this too. Actually, when we're plotting a course across, typically, another thing we have to kind of keep in mind is that each airport has its own kind of different ways to do things. So typically, if we were flying to Hana, the first thing that would happen is that the tower would direct us to stay offshore, typically to around Hana Point, and then come back in. So we could actually plot a 2-line course. And so if we were plotting a 2-line course like this, what would the first course be?
Kahului to Hana Point?
Right. What would be our heading?
It looks like roughly about 062 degrees.
Right. And then now we need to change to follow this line. So the first one was easy because we have this to help us determine.
The compass rose.
Right, the compass rose to help us determine what our heading is going to be. But how do we find this heading? And I wish I had a different picture of that computer, but again, it's going to be like a clear window that shows the degrees or whatnot. How would we set that down to show our next heading when we're plotting this?
Well, what you could do is do a notional extension of that line from Hana Point to Hana, and then you would put your protractor along that line and put the center of the protractor on that line of longitude that we can see just past Hana, and then you could measure the angle.
Right. So we would put it right on top of the intersection here, and then these will have 90, 100, whatever, and we would plot on that line too. And so the way we would do this is that we would plot the heading, and we would plot the distance by measuring using the ruler here. So that's one way to find out where we're going. There are two other ways that we can find out where we're going as well. So one of them is called pilotage. And pilotage is using visual references or landmarks along with some computations of time, speed, and heading and wind. So basically, if we were to use visual landmarks, let's say the old mill in Paia. So we would fly over and we would see that and be able to use visual references to determine how to get over to Hana. So things like the Paia Mill, big towns like Huelo. Over here at KNI, you would have you have that part that juts out here at KNI that you could use for pilotage. So there's a lot of different visual references you can also use to figure out where you're going. The last way to figure out where you're going is through dead reckoning, and that's using only time, heading, wind, and airspeed. There's no visual references used. Dead reckoning is by far the most difficult way to plot a course or to navigate. It requires doing the computations ahead of time.
You might just mention the distance scale.
So basically, each one of these here is 1 nautical mile. Okay, so tracking and recording position. We need to maintain positional awareness from takeoff to landing. It's always good to put your finger on the map and use visual landmarks when possible. So even as you're calculating through course and heading, you still want to be able to use visual landmarks to kind of double check to see where you are. You can ask the pilot or observer to determine position using GPS and or VOR DME, which I'll explain in the next slide. Once you locate a target, you must be able to pinpoint the location on the sectional and report that position to others. Since the details on the sectional chart are often not detailed enough to be useful to ground units, you have to transfer that information to a map. Knowing the aircraft's position at all times is essential if an in-flight emergency should occur. If you don't know where you are, then how can you find the nearest airfield? So given data from NavAids, we have to be able to track the current position of our aircraft and determine the position of ground features. So here's an example of GPS versus using a DME receiver. So to give you a little bit of background, the way a DME receiver works is that it tunes to a fixed position that's sending out a radio signal. So for instance, a VOR will send out a radio signal when you're tuned to it. And basically on your nav indicator over here, it'll basically tell you in what direction the VOR is. And then on your DME receiver here, it's going to show you how many nautical miles away you are from the VOR. And this allows you to determine a position. So for instance, if you have the map in front of you, we're to look at Maui 30 nautical miles away from Maui's airport, and the heading to the VOR was 040 degrees. We would know that we would be somewhere southwest of the airport, as long as the indicator shows it too, like this picture is showing here, which is this little arrow here. I'll explain this in a further slide. It's a little complicated to explain, but as you can see, it's much more difficult to find out where you are with a DME receiver than it is from a GPS receiver, because the GPS shows different parts of land, for instance, and let's say an airport is here, you know exactly where you are by looking on top view. Here's your plane here. So you know exactly where you are in relationship to the terrain when you're using a GPS receiver. So see these two planes here? As we saw on the GPS, it's really easy. On the GPS, we would see, like, let's say if this was Maui, we would see Maui, and the plane would be here, and then this would be the VOR or whatever point you're looking at or whatever. And it's very easy to determine where you are. When you're looking at the older system, which fortunately we don't have in our planes anymore, but it's basically a VOR DME system. What happens is that we have this radio transmitter, and we tune to it, and it tells us in what direction that radio transmitter is. So in this case, when we were looking at that indicator, this would show 258 degrees, and let's say this is the DME, let's say it's 12.5 miles. So the DME would show 12.5 miles, which is your distance. And by the way, it's not straight miles, it's slant miles. So the higher you are up, the further that actually is, because it's slant miles. And then it becomes very, very inaccurate when you get close. So you're looking at 256 or 258 degrees going in. And so on the display, you would see a 2, and then, which is that little kind of triangle thing. And then you would see 258 degrees. And then when you have an airplane here, you think, oh, well, it's got to be 110 degrees, right? Because you're going in the direction of 110 degrees, but that's not how it works. It's actually reversed, because it's telling you that this is the line here. So you're actually from 110 degrees. So it's a lot more complicated. It's very easy to flip it over and mess it up. While with the GPS, we can see right off the bat exactly where we are. And that's kind of the beauty of GPS. Okay, so now we need to talk about tracking and recording position. So what is the most prominent feature located at coordinates of north 20 degrees, 47.5 minutes, and west 156 degrees, 57.0 minutes? How do we find this?
I would say the first thing would be to find that latitude of north 20 degrees, 47.5 minutes. So you need to look at the scale for the latitude lines and put a little mark at that 20 degrees, 47.5 minutes.
We see here, this is 21 degrees on the map. And we're looking for 20 degrees, 47.5 minutes. Each one of these hash marks is going to be a minute. So we're looking at 47.5. We're looking at, what is it, minus 12.5, probably about right here. And then we're looking at west 156 degrees, 57 minutes. So we know this is 157 degrees here. And because it's west, which is, the numbers are getting larger as we go further west. 1, 2, 3, 57 minutes is here. So what feature is located at north 20 degrees, 47.5 minutes, and west 156 degrees, 57 minutes? It's Lanai Airport.